Hello and welcome to this video on topic 4. In this video, we will continue our discussion of random variables. In part 2, we'll look at the continuous random variables and their probability distributions. So let's start. In a previous video, we looked at discrete random variables, and those were variables where the possible values for the variable was actually a list of distinct numbers. That meant we could list the numbers in a table and assign to each of those numbers a distinct probability. We also looked at their distributions, their means, and their standard deviations. What we want to do now is look at continuous random variables that can take on any value in an interval. What that means then is that there are an infinite number of values that the variable can take on. Our ultimate goal here is to get to a special class of continuous random variables which we call normal random variables. These are important and they're also very common, and they play a very important role in statistical inference, which we'll get to later in the course. So let's look at this through an example that's somewhat made up. Let's suppose that we are working for the online retailer called Zappos. You may be aware of them. They're very well known for their sale of shoes. Let's suppose we're working for them and we want to look at data related to men's shoe sizes. If we were to look at all the possible sizes for shoes, we might see a distribution of discrete random variables that looks something like this graph. So here we have a histogram. You can see that each vertical bar corresponds to one particular shoe size, and in this particular histogram, notice that the shoe sizes are by halves. So here's shoe sizes of 11. Right here, this bar is corresponding to shoe sizes of 11 and a half, and this one here is 12, and so on. Now what we can do here, remembering that from our previous video, that in a probability distribution, all of the probabilities add to 1, we can actually talk about the area of this histogram as also being equal to 1. And what that means practically is that if we were to take each of these rectangles and compute its individual area, and then add up the area of all of the rectangles, we would get an area equal to 1. Now that's not very difficult to do because we have the length of each of the rectangles, we have the height of each of the rectangles, and so the area of each can be easily computed using length times width. And so, for example, we could look at this particular problem. What is the probability of randomly selecting a shoe size that is less than or equal to 9? Pardon the typo here, this should be shoe. So if we were to look at this on a histogram, it would look something like this. Notice we have all the shoe sizes once again here on the horizontal axis. Here we have probabilities per half size. And then you can see that each of these shaded rectangles represents one possibility that meets this criteria up here. These are all of the rectangles that correspond to shoe sizes that are less than or equal to 9. And so the probability of randomly selecting a shoe that is less than or equal to size 9 would be the sum of all of these blue rectangle areas right here. We're not going to be concerned too much right now with what that actual area is. We just want to get this idea that we can actually compute the area based on, we can compute the probability based on the areas that we see on the histogram. Now just keep this in mind though, this is not the same as the probability of randomly selecting a shoe with a size that is strictly less than 9. If we go back and look at that, notice because it says it's strictly less than 9, then we would omit this rectangle right here, which are all the sizes of size 9. So we'd look at just the ones that are strictly less than that, and then therefore we would get this smaller area here. So just keep this in mind. This is going to come back later. The area that we get from looking at strictly less than a particular value versus less than or equal to a value, that same value, are very different, or at least can be very different. Now, we just looked at a histogram where the sizes that were shown were in half-size increments. If it were possible for us to start making shoes in much smaller increments, let's say in quarter increments like 9 1/4, 9 1/2, 9 3/4, or even tenths, which of course might not be feasible at all. But if we could do that, the histograms that we would get would look very different and begin to actually look like curves. Over here on the left you see shoe sizes that are broken up by quarters, and over here on the right you see shoe sizes that are broken up by tenths. And clearly you can see over here there are a lot more rectangles because there are a lot more sizes of shoes to take into account. But what you want to notice here is that as you do this, the rectangles begin to trace out for us curves that look very symmetrical and very bell-shaped. And that's going to be an important idea that we're going to explore later. Now, what if instead of the shoe size, we examined the size of adult males' feet? How is that different? Well, men's feet don't come in just size 9 and 9.5. They can vary pretty dramatically, and they can be of all sorts of different lengths. And ideally or theoretically, they could take on an infinite number of values because each foot will be slightly different. What's important here is that we are not limited to distinct separate values. Once again, we can't put these into a table. We can't put this information into a table. Instead, what we do is we represent this with a probability density curve, which, as you can probably guess, looks a lot like the curves you just saw on the previous slide. So moving forward with this example, let's let the variable x be the foot length of adult males. So that's our variable that we're going to work with. And here's a first key principle. The total area under the density curve is always going to be equal to 1. So for example here, if we were to look at the probability density curve that looks like this, for the infinite number of values that the foot length can take on, if you were to completely shade this area here underneath this curve, trapped below by the horizontal axis, this area inside here would be exactly equal to 1. I'm not talking about the area of this yellow rectangle, I'm talking about the entire area under the curve. And we could say something like this. We could ask something like this. What is the probability that x is less than 9? To do this, we need to understand the idea that probabilities from a curve correspond once again to areas. So if I were to look at this density curve, what I'm interested in knowing is if I were to look right here when the size is equal to 9, so imagine a vertical bar here, and then look at everything to the left, I would want to know what is the total area trapped to the left of 9 between this curve and the horizontal axis. And so essentially what we get here is this picture. So on a probability density curve, if we want to know the probability that x is less than 9, we would need to compute that shaded area right there. It's bounded on the right by this vertical line that ends at x is equal to 9. Now let's go back here for a second and think about something we just said. How is the probability that x is less than or equal to 9 different from the probability that x is strictly less than 9? And what about the probability that x is exactly equal to 9? Well, if you were to look at the picture here, you would notice, hopefully, that there's not going to be any difference between the probability that x is less than 9 and the probability that x is less than or equal to 9. In fact, these are two interesting facts that come about from density curves such as these. The probability that x is less than 9 is exactly equal to the probability that x is less than or equal to 9. So in other words, this right edge right here, this boundary that we've set for ourselves, doesn't add at all to the area. In fact, we can think about it this way by thinking about this fact right here. The probability that x is equal to 9 is 0. Why is that? Well, if you think about it, since we're looking at an infinite number of values on the horizontal axis, then the width of the so-called rectangle when x equals 9 is 0. It has no width. It's just a point on the line, so that point has no width. So if you take that width and multiply it by this height right here, well, a length of some positive number times a width of 0 is still going to give you an area of 0. So the right edge here produces no new area for you, and so these two probabilities are actually equal to each other. Kind of interesting and odd, but it's a byproduct of the geometry involved. So let's take a look at a quick summary here of what we've talked about today. Number one, the probability distribution of a continuous random variable is going to be represented by a probability density curve. Second, the total area under a probability density curve is always equal to 1, corresponding to covering 100% of your possible values for your variable. And third, the probability that x gets a value in any interval of interest is the area trapped between the interval and the curve. So over here, if we look at this picture, here is a density curve for some continuous random variable, which we call x, and here's some interval for values of x. So if we want to know the probability that x is between a and b, then we would be looking at the area that is trapped between the density curve and the interval itself between the values of a and b. And of course, this is the blue shaded region you see here. So if we had some way to compute that area, and typically we do that with calculus, but if we had a way to do that, we could then compute the probability that we're interested in. A lot of the rest of this course is going to deal with how do we actually compute those probabilities, often with tables or with technology, and then how do we interpret them. So that brings us to the end of this video. I hope it was a little bit helpful in getting you introduced to these ideas. We'll continue with part 3 in the next video.